This presentation is primarily on annealing. It says annealing of electrical conductors, but the process and the principles apply to both ferrous and non-ferrous materials. This is the definition of annealing. Basically, it's a process that occurs after a metal, pure metal or alloy, is cold worked and then it's annealed. So basically, this is what happens during the annealing process. Now, even though I'll be talking about annealing, during the heating operation, 4 things take place. In addition to annealing, since the wire has been drawn, any residual drawing lubricant that's on the wire will evaporate. And if it's done properly, it will evaporate and not affect much staining or interaction with the wire that's being annealed. And if the annealing process is not done in a good atmosphere, of course, oxidation can take place. Now, in addition to removing the effects of cold work, other things happen. It says here impurities, dissolution, and precipitation. That means the impurities that are present in the metal can change, whether they're dissolved or precipitated out, and that has an important effect upon the final properties, and I'll show you this a little bit later on. So, annealing, what happens? First of all, there's a softening of the metals. Usually annealing is done for 2 primary reasons. One, because the wire is very difficult to process, so you have to re-anneal it in order to cold work it further without it breaking. And the other aspect is, of course, obtaining the original properties before it was cold worked. There are 3 stages, and I'll show them in the next graph, called recovery, recrystallization, and grain growth. Most people, when they talk about annealing, they talk about B, recrystallization, and that's where the properties, the mechanical properties, change. In addition to those 3 stages, the grains that are present will grow further and become larger, and that can also have an effect upon the resulting mechanical properties. This is a graph of what takes place during temperature. As you can see, at the top there are 3 stages: recovery, recrystallization, and grain growth. I've intentionally overlapped them because it's not a process where it goes from one to the other. Sometimes these things take place together. So at the beginning, in the recovery stage, there's a change in the electrical properties, and so the electrical resistance decreases. During that period, the mechanical properties don't change. During the annealing process, that's when you get a very large change in mechanical properties. As you can see, the elongation goes up, and you can see that the reduction in area goes down. For both the tensile strength goes down and the yield strength goes down. After it's fully annealed, in the last stage, the annealed or recrystallization grains grow up. Now later on, I'm going to show this slide again, because if you over-anneal it, this elongation curve at times may start to decrease, and I'll explain how that can happen later on, because that can have a negative effect on the mechanical tensile properties. This is a slide that was obtained on copper sheet that was cold rolled, and a picture was obtained while the sample was in a scanning electron microscope. When the sample was placed in, this is what the structure looked like, where it says rolling direction. If you could take a tensile sample from this region, it would have the properties of the fully cold worked, fully hard conditions. Now, after the sample was in the electron microscope for a period of time, it started to heat up and change, and then this picture was taken. So this region down over here, where it says recrystallized grains and annealing twins, are the properties of the fully annealed material. And if you could get a tensile sample here, you would have the tensile properties, tensile strength, and tensile elongation of the fully annealed material. Now this picture looks like it's about half of each structure, half annealed and half cold work. The temperature at which this took place would be called the Halfhard temperature, in which the properties are halfway between that of the fully cold work and the fully annealed material. Now, for information only, this is some data that was obtained on copper. And here on the y-axis is the annealing temperature or recrystallization temperature. And on the x-axis is the amount of impurities that are present in the copper in ppm or parts per million. As you can see, every single impurity that's dissolved in the copper increases the annealing temperature. And some are more harmful, have a greater effect than others. For example, bismuth. As you can see, 1 part per million of bismuth can raise the annealing temperature over 25 degrees centigrade. A very, very strong effect. So it's very important that if you're going to anneal a material, you know what the composition is. Not only if there are alloying elements, but also if there are impurities. Now, very often people get a chemical analysis, and they think if it's correct, that everything is proper and not a problem. But that's not the real world. When you get an impurity number, you're assuming that these materials are all dissolved in the copper solid solution. And you also assume that there's no interaction with the impurities. You also assume that there's no interaction with any oxygen that might be present. But in the real world, those things happen. And if those things happen, then the chemistry does not tell the full condition as to what might take place during the annealing process. In addition to that, sometimes what can happen is you get segregation. Some of the impurities that are present may not be dissolved uniformly throughout the matrix. They may be concentrated at the grain boundaries, and therefore you might get effects that have nothing to do with the actual value that you got for the chemistry. And again, there are sometimes solid state reactions. For example, lead is a harmful element in copper. Sulfur is a harmful element in copper when they're both dissolved in the copper matrix. But if they react with each other to form lead sulfide inclusions, then it's not as harmful because you don't have the maximum effect of each of these impurity elements. Now, how do you measure recrystallization? There are 3 ways of doing it. Sometimes people say, what's the annealing or the recrystallization temperature of this material? Well, you have to specify a time. And the logical time that most people use is 1 hour at an annealing temperature. Sometimes people do resistance continuous annealing, and so they heat the material during the drawing operation or during the strand annealing operation. And the 3rd way of measuring it is to put it in a constant temperature, maybe a furnace or a salt bath, and measure the properties as a function of annealing time. Now let's look at all 3 of these. This now is a graph that shows the percent softening or the percent recrystallization as a function of the annealing time, with the temperature being constant, the cold work being constant, and the chemistry or alloying elements being constant. As you can see, annealing does not take place immediately at the temperature. That's what's called an incubation period. Then, soon as that starts to go up, soon as the sample starts to anneal or recrystallize, it usually goes up in an S-shaped or sigmoidal type of a curve. So at the bottom, percent recrystallization, 0 means that's the fully cold work properties. 100% would be the fully annealed properties. Somewhat in between, where it's halfway, that would be the half-hard conditions, where you have the properties somewhere between the fully cold worked and fully annealed conditions. Now, what's a typical annealing temperature? Sometimes people say, what temperature should I anneal this material? This is a graph that shows different materials, copper, nickel, iron, silver, etc. The first column is the recrystallization temperature. As you can see, it varies all over from low temperatures to high temperatures, depending upon the material. But if you look at the last column, that tells you the recrystallization temperature divided by the melting point. And as you can see, the annealing or recrystallization temperature is approximately a third of the melting point. So if you've got some unknown material and you've never annealed it before, just anneal it for 1 hour at approximately a third of the melting point, and that would be good temperature for annealing the material.
Now let's review some key points from the video.